Reshare. Uh, can you see my screen now?
Yes, we can. Can you try and move the slides? Just
I
go
think-
for, okay, excellent. I think you're good to go now.
Okay. Sorry for that disturbance. Wayne Stephen Okello, and I'm here to present to you a project titled the Robust Cost-Effective Machine Learning-Based Diagnostics Tool for Beans Plant Diseases. This project is under the Marconi Research and Innovations Lab, and it's being funded by the Data Science Africa. Yeah, as we all know that beans are one of the most important components of our diet across the globe, but most importantly here in East Africa and Africa in large. So the objective of this project was to develop machine learning models for detection of more specifically bean rust and angular leaf spot diseases in bean plants. But also the other was to deploy these developed models in a mobile application, but as well as web application. Yeah. Yeah, so the data set that was used for this work was created by a team of researchers from the Makerere AI Lab, Marconi Research and Innovation Lab, and the National Crop Resources Research Institute in Uganda. And this was enabled by funding from the Lacuna Fund. So the data set was distributed as follows. It had three classes. That was the healthy with around 5,284 images, bean rust with 5,020 images, but also the angular leaf spot with 5,031 images. So this is just a glimpse of the health images from the data set, as you can see very crystal clear. Then on the bean rust, just to share maybe a preamble about this disease, is caused by a fungus, and it's usually characterized by symptoms of yellow or orange pustules on the leaves. And it usually thrives in warm and moist conditions, but it's most common in areas with high rainfall. But most importantly, unlike for angular leaf spot, as we shall see, it affects the bean plants throughout the entire season. Now, moving on to the angular leaf spot, for it, symptoms are majorly the irregular shaped lesions on the leaves, which usually turn yellow and eventually dry out, leading to defoliation or leaves falling off. It also thrives in warm and moist conditions, and also most common in areas with high humidity. But most importantly, also it's more common in the late stage of the season, unlike the bean rust, which affects common throughout the entire season. Of course, we did EDA, but a lot of EDA, but I'll just highlight this one, which shows the age distribution of the leaves or the plants that we have images of, and also tries to correlate with the analysis of the diseases in terms of age. As you can see, the angular leaf spot is the one in blue, and as you can see, it affects throughout
Have we lost you?
I'm off.
Yeah, so it seems like we lost the screen share.
Wait, sorry. Is it back?
Yes, it's back.
Okay. Yeah. So as I was saying, for the angular leaf spot, it affects usually in the late growing season, right? Unlike the bean rust, which affects throughout the entire season. And this can be seen. This can be seen in this distribution bar graph. Yeah, so of course went on to do data preparation and to make sure that our data is ready for training, such as resizing, which we did to 224 by 224, pixel normalization. This was very dependent on the models we are using. And we also split our data into train, validation, and test in the ratio of 70%, 15%, and for validation and 15% for testing. So basically, we used two techniques, that's two techniques of computer vision, image classification and object detection. So we shall start with the image classification. Here we employed the efficient net, but to be more specific, the B0. And we use the band size of 32, the learning rate of 0.001, and 500 number of epochs, and the momentum of 0.9. So these are some of these are the training, the loss and accuracy curves for the efficient net, as you can see. And this is it had test accuracy of 96% on the test data and the loss of about 0.139, and average precision recall and deference score of around 0.96 or 96%. Now, this is a confusion matrix. We have a number of a few misclassifications there, most notably between BinRust and ALS. So there's a bit of some misclassification, 26 and 24. Now, to make sure that we have a better model, we are able to retrain, but this time with an unknown class. We are using image classification with an unknown class, so that when you try to put an image which is other than BinRust, healthy, or angular leaf spot, it can tell you that this is unknown. On the previous model, if you just put, for example, someone kicking a ball or a human being or the sky, it will classify it among healthy, BinRust, or angular leaf spot, even which is not true. That's why we found it prudent to be able to include this unknown class. So this is a distribution of our new data set with the unknown class. Now, with the image classification with the unknown class, we use the three algorithms or architectures. We reuse the efficient net B0, the ResNet 50, but also use the mobile net, the version 3. The batch size of 32, the learning rate of 0.0001, as you can see, 0.9 momentum, but also we use ALS stopping so that the model automatically stops training when it has converged. Yeah, so for efficient net, these are the loss curves and the accuracy curve. On the left, that is the loss curve. Train versus validation. Then on the right, the accuracy curve. The ResNet, as you see, it is a bit, worse than, but these are the loss and accuracy curves for the ResNet. And these are the loss and accuracy curves for the mobile net. Now, on evaluation, We achieved 94.7%, almost 95% accuracy on test data. Efficient net model without the unknown class. Then we have a loss of about 0.157537 and an average weighted average precision of 0.95, recall for 0.95, F1 solve for 95% for the four classes, that is LS, BINRAS, healthy, and the unknown. Yeah, so this is our confusion matrix. As you can see again, as from the earlier model, is the misclassifications are mainly in the BINRAS and the angular leaf. Yeah, but on the unknown and health is a bit better. Yeah, so among all the models, EfficientNet performed better. As you can see, for ResNet achieved around 90% on test data. And this is a confusion matrix with a bit more misclassification, most notably for BINRAS and angular leaf spot. MobileNet also is around the same with ResNet, 89.89, which is approximately 90, the loss of 0.2658. And as you can see, it also has a bit more mixed classifications. As I said earlier, the best classification model we got there was actually the EfficientNet. Yeah, so these are some of the predictions from the EfficientNet model. And maybe I will highlight a few. As you can see, we have on the first column, that row, we have people playing football. They are actually children, and it's being detected as unknown, which is the case. Now, previously with the other model without the unknown, this picture would be classified as either healthy, angular leaf spot, or BINRAS, which is not correct. That's why we found it very important to include this. And you can see there is the sky and the road also unknown, but also the classes of LLS where it's predicting, right? And a misclassification, of course, of BINRAS with angular leaf. Now, as I said earlier, we used two computer vision techniques. So that was image classification, move on to object detection. And here, now that we are dealing with object detection, now, unlike the image classification where we are dealing with the number of images, now here we are dealing with the number of instances, because one image might have more than one instance of that disease. So this is the distribution. Again, we split the data into training, validation, and tests in the same ratio as in the classification. Because we had XML files for the labels, so we had to convert to the PyChartTXT that is valid for the YOLO V8, and of course we had to do the organization structure to align it with the way the YOLO model is expecting it. Yeah, here we basically use two models, that is the YOLO V8 and the YOLO NAS.
Wayne, just to let you know, 15 minutes are up. So if you can just highlight the key things that are remaining, and then leave time for some QA.
Okay, thank you very much. Yeah, so this is just the precision recall curve. And these are evaluation where we have the YOLO V8 outperforming the NAS for now. And these are some of the predictions from the object detection. And we deployed our models on a web application using Flask and mobile application using Flutter. Then currently we are optimizing the mobile application, but also we intend to deploy the models on a dedicated hardware module. But also we plan to carry out field tests to validate our models. And we are writing a paper about this work, which we intend to submit very soon. Thank you very much.
Thank you very much. I think there is already a question on the chat, and feel free to raise your hand and ask some questions. So you can see there's already one from, I believe it's from Shegun.
The one which says, I would recommend that includes being with other chat. Okay.
So maybe Shegun, would you like to ask your question?
While he was presenting, I saw a distribution of the diseases, the two diseases which he was looking at, and I found out that the chart shows that in the 8 months you have quite a lot of those. So I was wondering, can we make conclusion that this disease happened during that month, or maybe the images you got that were collated were more in that month? So I'm just wondering. I just want to be clear on data set itself.
Okay. Thank you very much. First of all, before even coming up with that chart, prior research and consultations with these experts from NACRI, it had been indicated that there is that sort of pattern. So from also the images we got, and we tried to do a distribution, it brought out the same picture. So it's not necessarily a conclusion, but sort of using the prior knowledge that was given by the experts, and now comparison with the data set. But the actual picture is not a conclusive thing. I don't know if I've answered the question.
Okay. Yeah. Then the other question is, I see that you are classifying healthy disease and the other one, but the unknown. I'm still wondering why is your system trying to classify unknown? I'm just wondering, why do you have the fourth class, which is unknown?
Thank you very much for that wonderful question. Yeah, so what happens is that usually when, for example, you have deployed these models, maybe on a mobile application, and you have given the farmer. So one time it happened, not on this project, but one project that we are doing on passion fruits. So sometimes the farmers can just get any image, maybe the sky, and or the road or whatever. And what the model will do, it will predict regardless of whether it is a plant image or a disease image or a health image. So it will bring, for example, bean rust. And these farmers will be like, you guys, you people are giving us wrong things. How can you say the sky is bean rust? So that's why we are trying to come up with a technique where if it's none of these classes that are expected, the rest should fall under unknown. I don't know if I've been able to answer your question.
Very well. Thank you very much.
Yeah, thank you for answering those questions. Maybe you can respond to a comment on the chat as we then move to the next presentation, which I believe will be by Godliver. So there's a question on the chat, so it's actually a recommendation. Can you read it?
Yes.
You can respond to it.
Yeah, actually, yeah, thank you. I think this is very insightful. because it will also cater for, not that every bean leaf is in all the 4 categories, in the 3 categories. So I think it's very insightful, and I'll try to talk to different partners where we can be able to get these images to include in our data set. Yeah, thank you very much, Kadeg. Thank you.
Okay, and thank you very much. I think can all show our appreciation for the speaker. And then I believe Dr. Gottlieb, I saw you, so you can begin to share. If you have any more questions for Wayne, please put them in the chat and he'll be able to interact with you on the chat. Okay, so as soon as you're ready, you can go ahead. You have 15 minutes, so 15, and then we have QA.
Thanks, Sarah. I hope you can hear me.
Yes, loud and clear.
Okay, thank you. Yeah, so I'll be talking about the work we've been doing for the past few years, and also related to low-cost spectrometer. So this project is built on the previous grant that I got from DSA, and purposely wanted to investigate on the low-cost devices for crop monitoring. Yes, so yeah, so I come from Busitama University. That's where I teach, and also I'm a member of the AI Lab Makerere University. And my PhD was related to crop monitoring, and which became an extension of what I'm doing apparently. So if you're wondering where I'm based, that's the location, very in the middle of the forest. So that's where Busitama is located. And we're also very lucky that we have the smallholder farmers. If you look at our map here, people we can always reach out to when we have our tools, and we want to get feedback from them. Yeah, so spectrometry became the key to this study for, I think now, like more than 5 years. Yes. Yeah, so we thought it would be one of the technology we need to use to substitute for visual symptoms, where we know we have agricultural experts visiting farmers, telling them there are such kind of problems in their gardens. But also our first innovations were based on mobile devices, and these are based on visual symptoms as well. So we thought spectrometry can give us an extra eye or a better eye to see things that that cannot be seen by our naked eyes. So in my early work, we are able to see that at least by 6th week of plant infection, we can be able to track the disease. And this is just like a graphical view, but there are more findings under this study that we did earlier. So with this study that we did, we're using high-end spectrometers, which are very expensive to use, even to employ here practically. So that's why we went into low-cost spectrometry development. So here I've been working with one master's student. He's called Joshua from Makerere University. And we defined some set of things we needed to do. This is the early version of the work that I did. And so we needed to enhance on this tool to be able to understand the information that comes from it, also to validate it with other devices or other tools. And so we started from scratch, like you see there, oh, that's a set of things, all ideas together. And then we had to model a tool in this work that looks like that. So it's from low cost material, which includes grafting. Then, if you look at down here, we employ a local device, that's a CD, and then we pass light through that, and then we employ some other mechanism here, how we're going to pull out the light to mimic the high-end spectrometer. And then at the end of the day, our early challenge from this work was how to control the light that is coming out of this device, and then have a clear spectrogram like what a high-end spectrometers give. So we've been able to achieve this in this work, and with our second prototype, I think with the first prototype, working in the field. And yeah, so our motivation still is behind the features we extract, how we localize the subjects, and then capabilities of zooming in, and also knowing that the relevant features of that are related to disease diagnosis. So if you look here, this is the previous work that we, okay, this is the high-end spectrometer, what it gives us. It gives us relevant features that are related to disease monitoring. And so, so this is where we are with the low-end spectrometer. And we realized that the most relevant features for cassava, AG cassava disease diagnosis, that is with a mouth class, is around 500, 600 millimeters. NMS, sorry. So same applies here. This is the center of our focus to see what are the most relevant features for this device, and even how best we can have a shorter wavelength or specific wavelength that relate to the disease. So we did this, and we had an experiment in this work that was in a controlled setup that looks like that. When plants are really young, they don't look like this anyway. We plant stalks, and then until they get up to almost above our height, some varieties. So we're able to pick some data sets, data types, I think, yeah. So able to pick some data types with the low-cost device, with biochemical, those are the agriculture, the lab chemical data. So we pick a sample and analyze it, and also able to use our camera phone, like we said. This is still like after the experts, so we have people using smartphones to take images and analyze them, and also able to employ the device that gives us photosynthesis data. So with this, we've had some findings so far which are very promising, because initially with the tool we had, we only tried to do some sort of a binary experiment, like we have one disease and the other and all that. But here we've been able to do a multi-class classification on cassava diseases. And then also we've done some preliminary work with imagery data sets. And so you can see we have 63% versus 88%. And these are plants which are grown in a greenhouse where we have less of the visual symptoms. So we have more findings here, and also the whole process, like which classifiers we employed and versus what. So you can be able to look at our short paper there. And then we've also been lucky to present findings of this work to different places. That was Kigali AI4D conference, and then we've also been able to share our findings with various communities, like schools. I really find that this knowledge is very important to pass on to the young people who are very inquisitive to know what happens with these devices. So yeah, I think that's it. And then we have quite some resources. with data sets openly available from the first project we had to this current one. So you can be able to access some of our resources already online. And we've already gotten some good feedback by the spectroscopy data, with some people contacting us on how they want to use the data. We already have guidelines how they can use it, but then some people are already using it well. So I think it's good for the communities who want to explore more into spectroscopy and disease monitoring. And then I think I end by thanking all the Data Science Africa for giving us all these supports from the first grant, then other collaborators, Makerere University and other partners that have been able to support us in one or the other. Thank you very much.
Thank you so much. Thank you for that presentation. There's enough time for questions. Any questions? Maybe if I can ask first, so the data that you're now collecting, it looked like the spectrometry data, it wasn't as accurate as the visual from the imagery, right?
Yes, so the data we are collecting looks like this. These four items, spectroscopy, biochemical, and the visual still, yes.
Wasn't the strength of the spectroscopy the idea that it could capture it before the visual can see it?
Wasn't the again?
So isn't one of the strengths of the spectroscopy approach that you can actually detect the disease before it has a visual signs?
Yes. Yeah, that's the whole hypothesis for this work, that we should, because if you look at these plants that have grown, we actually stop the experiment once we see the symptoms like this.
Okay.
So, however, we are supposed to detect the disease before it is visual, they're seen by, symptoms are out. Yeah.
Okay, so how exactly then would you do that testing of that to see that of that hypothesis?
Sorry, there's some people making noise, but I can't hear all the words you're saying. How? On my side, anyway.
Oh, okay. So I'm saying, then how would you validate that hypothesis in terms of if now it's very interesting that even at the end, when the visual symptoms are there, it seems it's less accurate than the imagery. So how is its performance when the symptoms are not yet visible?
Okay, so one of the things we are employing is, of course, is multi-model kind of approach, that we need to have all these data sets combined to see, to give us an added advantage. So in the end, we won't only look at spectroscopy, but we can also look at what a combination of all these data sets, give us a better prediction than even only spectroscopy. So that's the whole hypothesis, like in the end.
Okay, thanks. I'm opening the floor for more questions. Okay, I hope that means that everybody has really understood what is happening, and any other questions you can have them on the chat. Fine. I guess a final one would be, now this was a controlled experiment. Are you moving now into the field, into the farms?
Yes, so the next step is to move to the farms. We have really collected data outside the spectroscopy, the screenhouse with in gardens, but it's not too much. So we are meant to have like different maybe spectrometers out for testing, which should also have the different spectrometers out for testing. That should be the next thing. And how people can easily use them, because now we've been using them like as a lab or as a team.
Okay, thank you. I think we can appreciate the speaker. And then if you have other questions, use the chat functionality. So next up, we have Alex, I believe, and I think I saw him.
Yes, I'm here.
All right, excellent. You can then share your presentation and begin to make it.
Yes, can you hear me, please?
Yes, I can hear you.
Yeah, can you see my screen?
Yes, we can see it. I don't know if you want to make it full, like presentation mode.
Yes, please.
Yes, and then if the slides are moving from one to the next, I think you're good to go, and you have 15 minutes.
Yes, thank you. So I have quite a number of slides, so I'll try to be fast enough. My name is Alcado Alex Barakabis. I'm from the Department of Informatics and Information Technology at Sokoine University of Agriculture in Tanzania. So my presentation will be focused on previous works, current works that I've been doing regarding related to crop yield prediction, monitoring, Internet of Things, agro things, how we can help smallholder farmers. So I just jump quickly into some of research challenges which motivated me to. So as we know, smallholder farmers almost in every maybe African country employ about 7% of the population, and of course they produce. They contribute a lot to the GDP. For example, in our country, agriculture accounts for 26 up to 30% of GDP and employs more than 80%. But there are some of the challenges facing farmers. So some of the challenges include, for example, field monitoring, how to maximize their crop productivity, how to irrigate, how to select crops based on a farming condition or climate condition in different regions. So my research field is on the like field monitoring, crop yield prediction in the context of smart agriculture. So I also focus on maize crops, and see how crop yield prediction models, monitoring using digital tools can help smallholder farmers. So actually, the research objectives that have been working in projects here at Sokoine University, so include the development and the overall design of machine learning based Internet of Agro Things, a smart farming system development for smallholder farmers using these IoT sensors. So I have been also developing or working on sustainable farm scale crop yield prediction models development that can help farmers to for early season or end of season prediction to predict their crops. So I'm also trying to develop some new artificial intelligence based strategies, policies, different frameworks that can help smallholder farmers to adapt the digital technologies. So this is the crop that I'm focusing on. So one is maize crops. And why maize? Because most of farmers are involved in maize crop production in the regions that have been working on. And you know, maize is one of the staple food, of course, which most of our communities depends on. The methodologies that and approach that have been working on. So this project is being carried out in Morogoro in the Mwanza region. So we have two districts where I'm specifically focusing on. So it's Kilosa and the Gate districts. So from Morogoro and the Mwanza. So, and the smallholder farmers that I'm focusing on those actually rated to having 1 to 5 acres. And you see from the user requirements that I have been conducting. So some of the data that I have been working on include the agricultural IoT data. So these are the data actually generated in real time by sensors which are installed or configured in smallholder farmers, as you see in the next slides. So I also collect agriculture or yield data. So these are the data that I collect from the Ministry of Agriculture. So based on using the previous agriculture yields of maize from previous years, say 10 years back. So I have managed to collect this data, and these are some of the activities, field visits, when we are interacting with the farmers, collecting their user requirements, for example, and see what they need in terms of the digital tools that we can develop for them. So we want to develop something that we have contribution of farmers themselves, and not only developing or designing something which is no farmers or user interference. And these are the farmers from Geita region. When we are going to meet with them and see what are their views, what do they need in terms of the digital solutions, how can they help them. So manage to collect their views. And these are just some of the preliminary findings. So from the user requirements themselves. So you can see based on the field visits that I did. So for example, I was asking farmers on which types of crops they grow mostly. So it came out is maize and beans, as you can see in this graph. So maize took a very, very large number. You can see rice, and that's what actually motivates me to work in the maize crop. So we were also asking farmers to identify their farm size. You can see most of them mostly working on 1, 2 acres, maybe 4, so up to 10 acres. So 13 to 30 acres, there are very, very few, maybe 1 or 2 farmers who, most of them works actually in 1 or 2 acres. So, and that's our focus for small holder farmers. So we don't want to work on those big farmers because they have actually the tools that can help us in their agricultural activities. So we're also asking farmers the measurement tools that they use. So they're actually using pacing. You can see estimation or prediction, what they use. So there is a very, very challenging issue in terms of estimating the crop yields or predicting the crop yields. So they're still using the traditional methods of estimating or predicting their crops. So the means of measurement or counting of sacks, for example, they use, so they just normally count sacks, like 1, 2 is just the traditional method that they use. So for example, this one identified 8 sacks. Sacks. So there's no digital solutions that can help smallholder farmers to monitor or to predict their crop yields. So asking them to identify the quantity of sacks produced. So you can see most of them identified 6 to 10 sacks that they produce based on their traditional ways of farming, of doing farming practice. So that's where we came to see that there's a knowledge gap that needs to be bridged. And then we now started to, based on the data and user requirements, what we saw from the field, we started now developing a machine learning based IoT smart farming monitoring and management system, of course, across Africa. So we have been developing an IoT and machine learning driven system which can help farmers to actually to monitor the crops performance growth and predict their yields. So we employ machine learning and the big data analytics to analyze different patterns, insights, and predict farmers so that it can help them in making a good decision. Say when they can know in very, very early stage that they would the yields, the crop yields will be this much, then it can help the smallholder farmers even in budgeting. And when it comes to national level, it becomes also easier for the governments, for our governments to make a good budgeting for their people. So this is actually the mode, the prototype that I have been working on. So you can see we have a soil moisture sensor. These are the sensors we install, and we also use a solar panel to provide the power to these sensors which are installed in the farms. So we collect a lot of data generated by these IoT sensors. We have a lot of IoT sensors, including soil moisture, temperature sensors, and weather station sensors you see in the next slides. So we collect this amount of data and upload them in the cloud storage. So based on this data we collect, of course, including image of crops that we take using this camera, which are inserted or installed also in the farm. So based on the data that we collect, we develop, of course, a lot smart apps which can be used by smallholder farmers, and we also develop crop yield prediction models. So we rely on this data which are generated by IoT sensors and the data that we have collect from the Ministry of Agriculture. That's the yield data. So this actually the field practice that we have based on the prototype. So this is an example of the soil moisture sensor we install in the farms, and this the solar panel, so which provides energy to this to these cameras and IoT sensors which are installed in the farm. So we have been collecting data, our own real-time data generated by these soil IoT sensors. So we want to rely on our own actual data that we collect in real time. So we have been collecting this data since February, but we have, of course, the data which we have already collected, and we are now, because the planting season is starting here in Tanzania from this October. So we want again to start collecting from October to February next year. And then when another second planting season starts in January or February, we'll be collecting another IoT data from February to June next year. So this is what we have actually been doing in the field. And this is the agricultural weather station that we install in the field, collecting the data. So you can see the real-time data collection and image pictures taken by cameras which are installed in the field. So we have preliminary results and different outputs from our research activities that we have been doing. And one of the research findings that we have, so you can see these are the data which have been collected. So you can see this have been collected in July. And this is just a snapshot of the data, but there are a lot of them which, of course, have been also uploaded in IDRC dataset storage. So I can share maybe the link after the presentation. So you can see temperature, for example, humidity, heat index difference, and many other data. And you can see, of course, the graphs, how this data parameters changes. So this is the soil moisture, how it changes in real time. This is the wind speed, how it changes in real time, based on the from the IoT sensors that we have installed. So this way it becomes easy for smallholder farmers to know. So we are trying to do this so that at least, because most of farmers now have the smartphone, so they can actually know and come and become easy for them, to know when the water level drops in their farms, so that probably they can perform irrigation, smart irrigation, they can irrigate, or when the water level goes up, when the temperature, for example, when the humidity, or when the heat index in the farm, because these are all actually affecting parameters of any crop when they are growing from planting to harvesting. And this actually it's not like the machine learning prediction that we are currently developing now. So we are just trying to use one parameter, the soil moisture sensor, and see how the actual and the predicted value based on one parameter. So we are currently developing now the crop yield prediction model. So based on the data that we have collected, and hopefully next month the crop yield prediction model will be finalized, and the work is actually ongoing since we have already data that we have collected. But the crop yield prediction model will be is actually ongoing process, but we'll be developing based on the data that we have. But we want to have enough data that we collected from October to February next year, and February up to July next year. So we want to have large amount of data sets that we can use, so that we can have a very good accurate crop yield prediction model. So this is again yes, thank you very much. So this is again the IT.
So just
just winding up. So this again the cloud IT dashboard, as you can see, based on the parameters. So this what we are currently on in terms of developing machine learning IoT monitoring and the prediction models. So in terms of conference, so we have achieved 3 conference papers. So one was presented in June at the SUA Annual Scientific Conference. This is the conference organized by Sokoine University of Agriculture. So I've also been able to, one of our papers has been accepted in the IEEE 50th International Conference on ICT for Development. This will be in Ethiopia, Addis Ababa, in October next month. So it's all from this work. And last year, December, was also able to present machine learning Internet of Agro Things adaptive smart cloud farming system for smallholder farmers in Tanzania. This was ICTA EMOS, which will be published by Spring Nature. I think from next, the paper is being presented, accepted already for Spring Nature publication. So we are actually also working and finalizing one of the comprehensive work covering digital and data-driven agriculture to increase food security in Africa. We want to see how we can harness the power of disruptive technology. So AI, IoT, and remote sensing technology. This will be a very comprehensive work covering a lot of activities in terms of digital and data-driven agriculture across Africa. So in terms of training events, outreach activities, so I've presented some of my findings in one of the national agriculture exhibitions called Nanerani in Tanzania last month. So I have presented also some of my findings and the works in the African Leadership Champions in AI and the Human Computer Interaction Summit in Cape Town. This was also last month in August. So just my takeaway to the audience is let us try to transform our ideas into startups and see how we can save the local community. Thank you very much for support from DSEI. Thank you very much for listening. Thank you very much. This marks the end of my presentation. Thank you once again.
Thank you very much. We have a few questions. Maybe you look in the chat, and as you read the ones in the chat, Shegun, I see your hand is up.
I want to very good work. I just want to add, looking at the data set, I believe one thing is that at the end of the day, when we collect some of these data sets, we should be able to use it to, develop a very good model so that some of our farmers can use this model to help their life and help their farming. But I was just wondering, I don't know, does your data set cover, because when I look at it, you're trying to collect data set that has to do with crop, but does it take into account the yield of the crop at the end of the day? Because I believe if we are collecting humidity, soil temperature, and the like, we should also be able to, collect the yield at the end of the day, so that mapping the yield to, the various weather patterns will be able to develop a very robust model. So I'm just wondering, does your data set also put into consideration the yield of the crop based on the data you have collected?
Yes, thank you very much for your question. Yeah, we actually not only we don't only rely on data generated by IoT sensors, but we also collect the agricultural yields of maize, and so we have also that data. Maybe I can also share that data for yield that we have collected. So we have of that data, we take that data into account, and we have the data.
Okay, have you seen the questions on the chat?
Yes, very good presentation. The OV767 has low resolution, what might generate noise, and it's also how do you manage with this limitation for night vision, vascular disease? Yes, thank you very much. So it's just available in the prototype, but that's not the camera we actually use. So we have a very, very good camera with a high resolution. That's we use to take pictures of the crops. So that's not the camera we use. Egasmando.
There is another question on the chat.
So how does the real data correlate with the machine learning data? So we use the real data to feed to and use machine learning to develop crop yield data. So we actually use the data and develop crop yield prediction model. So we use data as the input, and there is no actually the machine learning data that we produce out of it, but we use the agricultural data and the IoT data that we generate from IoT sensors to develop machine learning prediction models. So the machine learning data, the machine learning uses the data we actually collect. I don't know if I've answered your question, Bramwell.
Okay, I think the conversation can continue on the chat. Just in the interest of time, I would like to invite, first of all, we thank you very much for your presentation. And then, so we appreciate you and thank you very much for the excellent work and the presentation.
Yeah, thank you. Thank you very much.
And also, I think you've called people to action, that people should also think about, you've mentioned something to do with startups. I think that's an interesting take-home message.
Yes, and that's what I would actually like to maybe to like a takeaway message. Let us not only work on our projects and put things into our cabinets. So we should try to transform our ideas into startups. So that's my very, very takeaway message wherever I go.
Okay, so thank you. So I believe the next presenter is Emmanuel from the University of Ghana. So you're free to set up. I see Lighton, you had unmuted. Is there something you wanted to say?
No, that was just a mistake. Apologies, sorry.
No problem. Emmanuel?
Hello. Yes, please.
So you're ready to present?
Yes, please, I am.
So you can share your screen and then you have 15 minutes, starting as soon as you display your screen. So are you able to do that?
Yes, I am.
Okay, go ahead.
Please, can you see my screen?
I can't see any. Yes, it said you're viewing. Says I'm viewing your screen, but there's nothing on it. It's just black. Okay, now there's something.
Okay.
Maybe you can check if you can move from one slide to the next. Perfect. I think you have 15 minutes. It's 15:07. So yeah, I'll jump in if you exceed. Thank you.
Okay. You're welcome. So my name is Emmanuel from the University of Ghana, and I'm working on a revisit of the extreme value theory in the management of a hydroelectric dam. My work is sponsored by the Data Science Africa. So I'm going to move to the next. And this is the outline of my presentation. I'm going to start with some introduction, and then I'm going to go all the way to some steps for future reference. So on my screen, there are two disasters. On my left is an earthquake in Turkey, and on the right is a flooding in the Amazon. These are all very disastrous events, and because of their nature, they don't happen often. And because they don't happen often, we barely have much information about them to study them. So conventional statistical techniques, which mainly use the mean, are not able to capture these kinds of data. So then there comes the need for a technique in statistics called the extreme value theory. Now, extreme value theory is a branch of statistics that is used to model extreme events, as I have described earlier. And it is applied in many areas, from finance, insurance, geology, even in sports. And applying this to my project, which is focused on the Akosombo Dam, as we may all know, a dam is a huge infrastructure that is built on a water body to store water for purposes such as water storage, for generating electricity, controlling flooding, and so on and so forth. So in this work, we are focused primarily on the Akosombo Dam, which is the leading source of electricity in Ghana. So the problem my problem is there have been many researches in the area of the dam, the Akosombo Dam. We try to model the water levels, but none of the research so far has considered the possibility of truncation. So this work seeks to consider all of those effects and also redo what has already been done and then compare what we get from truncation, considering truncation to what has already been done. So below are three objectives, as I have said, to provide a model that will describe the extreme elevation of the Akosombo Dam, taking into account truncation, and then to also compare with existing ones. And we would also try to estimate high quantiles for both with the data we have and then with the data we are going to reconstruct. The data source is from the Akosombo Dam, and it is the maximum water levels of the Akosombo Dam between the years of January 1966 and December 2013. So a brief review of what has been done. Minka 2016 used extreme value theory, which is divided into primarily two schools, but he used the generalized Pareto distribution to show that the expansion of the dam can reduce the probability and also prolong the return period of floods around the Akosombo area. Okran also applied another distribution in extreme value theory called the generalized extreme value distribution to also model the monthly minimum and maximum water levels of the Akosombo Dam. Primarily, there have also been papers by Aban et al., Newt 2010, and so on and so forth, who drew the attention of possible truncation in Pareto tail modeling. Bayland et al. Also proposed a model that can help us to capture truncation and also reconstruct the parent distributions. So in light of that, Ma et al. Also applied what was done by Bayland et al. In the area of earthquake frequency in China. He applied the truncated peaks over threshold distribution to predict the earthquake frequency and also the return periods of earthquakes in several Chinese zones. So this is a brief intro to the methodology that we apply. We say when we let X to X, X1 to Xn be an order of independent random variables, then we can say that the focus on the model is, we are focused on the maximum at the moment. We can also look at the minimum, but we are interested in the water level that is going to cause an overtop of the Akosombo Dam, in the sense that hot water level is going to go over the maximum water of the level of the Akosombo Dam to cause flooding and potentially destroy the dam. So that is the focus of this research. And so to be able to find this, we need to characterize it with a distribution. And there have been works on it. Gnedenko developed the extreme value distribution, which I have labeled as question 3 over there. Now, this distribution was okay, but it was very difficult to work with. So Jenkinson introduced the generalized extreme value distribution, which serves as an umbrella distribution, in the sense that in extreme value distribution, we have domains of attraction. So for Gnedenko, in the extreme value distribution, you need to select all the domains of attraction and then fit it to the data and then compare. But Jenkinson introduced the GEV distribution in the sense that why not have an umbrella distribution, which will rather tell us the domain of attraction, making work easier for us. But it was difficult to work with. So in the sense that it used only the maximum, it divided the data into blocks, which could be months, and then chose only the maximum in each of the blocks to fit the distribution. And because of that, it was known to waste data. So Jenkins, Balkema, and Dehaene introduced the GPD, or the generalized Pareto distribution, which rather than selecting the maximum in each of the blocks, you select a threshold and then select all the values above the threshold. And that will be your excesses, the exceedances. And you use that to fit the model. So, as I said, my work is primarily based on testing the effects of truncation. And I have defined truncation over here is when observations below or above a certain threshold are not included in the data. So a random variable Y is said to be truncated above, if above that threshold, you don't have values, and it goes for the other way around. And the distribution is as I have listed in the equation 6 here. So this work, we are going to implement the maximum likelihood estimation method outlined in Bayland et al. In 2016 to estimate parameters of interest, which I have listed there. That's the shape parameter and the tau. So parameters of interest, which we are also interested in, are the return level, the return period, and then exceedance probabilities. So before we did everything, we had to do descriptives of the statistics of the data we have. And looking through the descriptive statistics, you can observe that the data is skewed over here, negative. So that gives us a go ahead to fit the data to work with the data. So fast forward, we fitted the generalized extreme value distribution using both the maximum likelihood estimation method and then the Bayesian estimation methods. And we had outputs as I have shown in the table, in table 2 here. We also did the same for the other distribution, which is the generalized Pareto distribution. And we had results as I have shown over here. And then we went ahead to fit it for the truncated model. So this is the truncated model, and then the parameters of interest I have listed over here. So we can observe that the truncated generalized Pareto model does better than both the generalized extreme value distribution and then the generalized Pareto distribution. We can observe even from the confidence intervals, because in extreme events, we are mostly focused on accuracy. So we would want an estimator, which is going to rather a model which is going to give us small confidence intervals, because we cannot risk having large confidence intervals. And observing from all of these, the primary parameter of interest is this one, which is the shape parameter. And we can observe that for the truncated generalized Pareto model, the confidence interval is the smallest amongst all over here. And then here as well. And then the same over here too. So upon that, we estimate other parameters of interest, as I have said earlier. The return period is the time that it will take for us to record a certain level. So we have the return level. So in this research, we want to know how much time it is going to take for us to get this height. Also noting that the Akosombo Dam's maximum height is 278 feet. So with the output over here, for every 2, we can expect that we will get a return level, or the water level in the Akosombo Dam will be at 273 feet, 0.57 feet. And the exceedance probability is the probability that is attached to the return levels and then also the return period. So we can say we have 50%, we have a 50% chance that we are going to have at least this 273 feet in 2 years. So we can go all down the way here and then observe that for every 100 years, it is going to take about 100 years for we to get to this maximum level. And the probability is also very small. So what do we take from this work? We have considered truncation at high elevation levels in the estimation of the extreme value parameters. And then, as I said earlier, the right truncated peaks over threshold distribution yields a smaller confidence interval, which is what we expect from, we prefer in extreme modeling. Sorry. And also because due to the exceedance probabilities, there is a very small chance that the water would exceed the dam's crucial maximum water level. Because when we check over here, we can see that as we go higher, the probabilities fall. So the probability, as before it will get to 278, the probability would be going down and down and down. So although dam engineers can say the dam is safe for now, they may consider increasing the height of the dam so that we would avoid any possible overtoppings in the future, as has been happening in other parts of the world. So the next steps for this research, we will be considering some simulation studies and also paper writings and conference presentations. Yeah, some references. Okay, I'm done. Thank you.
Thank you very much. Let's open it up for questions. And are there any questions on the chat yet? Not yet. Okay, there is one. Moses Dega, please go ahead. You can unmute and ask.
Yeah, just wondering, listening to the point of the work, which is to prevent the dam exceeding the water level. Dams have spillways to do exactly that. Would you be implying that that mechanism is not working because we've not had any actually dam exceeding unless they don't have a spillway? Just comment. Thank you.
Yes, so dams do have spillways, but we are considering the case where, because recently there was an event in the US where the spillways were destroyed, and at the same time there was a lot of rainfall. So at this particular moment, it was very crucial. The steps to take was very crucial because the dam management had to decide on whether to allow the spillways to get destroyed or open it or risk the overtopping of the dam. So we are considering the effect that, as I said, truncation effects. We are considering truncation in the data. Earlier, truncation was not considered, but we are considering the fact that if there is no truncation, if the water level is allowed to go above and above and above, what is going to be the outcome? So that is the primary area of this research.
Okay, I'm curious, the data, what data did you use to fit your models? And over what duration was this data?
Okay, so this data was obtained from the Akosombo. So the Akosombo Dam is, so the data source, it was obtained from the Akosombo Dam.
Yeah, I missed that. Okay. And in all that time, it has never overtopped, thankfully.
Thankfully, yes. But it has gotten to the, some critical levels, but mostly they open the spillways for the excess water to pass through.
Okay, Mike, one question I would have, is there interest in linking this to like prediction of like time series prediction of the water level, and then seeing the possibility that it will overtop in the future? I don't know if the future here would be maybe a short horizon or less, and therefore you can then take actions. Is that something of interest?
Yes. But there have already been researches, the same data, some people consider using time series to analyze, but we are considering the concept of extreme value theory, which is more appropriate for these kinds of data. But there have been works using time series.
Okay, and just out of curiosity, this does not depend on the underlying distribution. So you can apply it to whatever the random variables, whatever the distribution. Does that make sense?
I didn't catch your question.
So you base this on, when you are defining extreme values, you had this series of random variables.
Yes.
Now, does the underlying distribution of those random variables feature anywhere?
Yes. So, okay, over here. Yes. So this is what we say. We assume that X, which are in this case, the water levels, follow an order of independent random variables with a common distribution function F. Okay, so earlier we only took the maximum here, but the maximum over here, as you can also see here, depends on N, which over here can be the time. So if you are using this probability distribution here, as the time increases, the errors would also be increasing. So we want to have a distribution that is not directly based on, because over here we have an exponential distribution, so the errors will be will be increasing exponentially, which would affect our probability distribution. So we want a distribution that does not directly relate to the number. So over here, the number of years is not really affected by it doesn't affect the distribution directly. But in this case, the n affects the whole distribution as it increases.
Okay. I think, thank you for that. I think we'll take anything else offline, but thank you very much for your contribution and your presentation to us. Thank you very much. I think it's now time for the final speaker of the day, Asefa. I believe it's Asefa.
Yes.
Okay, so I think you can share your screen. So maybe you can put it in presentation mode. Yes, and then
Can you see my screen?
yes. So you have 15 minutes.
Okay. I'll cover in 15 minutes. Okay, thank you very much. My name is Yimar Asafa from University of Nairobi. I present the progress review for the junior researcher. My title is the evaluation of the skill of seasonal and temperature forecast from global prediction system. Introduction, data and methodology, result and discussion, finally conclusion and recommendation. For the introduction, Ethiopia is one of the states more susceptible to the climate crisis and variability, with a significant consequence for in agriculture productivities. In Ethiopia, there are numerous natural hazards, including droughts, floods, volcanoes, and earthquakes happen in different times. In seasonal forecast for Ethiopia, it categorized based on distribution and volume rainfall. There are three. The first one is October to January. This is Baga season in local language. And February to May, it is a bulk season. And September to June up to September, it is Krampt season. It is the main rainfall season. National Meteorological Agency of Ethiopia seasonal forecast made by the analysis of past involvement and condition of atmospheric, oceanic, cyclonic scale, and climate factors. The NMA, National Meteorological Agency, starts for the seasonal forecast from 1987. It is a type of using analog method. That means it uses for the in-soil conditions, surface temperature, and teleconnection systems. Then National Meteorological Agency, the seasonal prediction systems are normal, above normal, and normal condition, above normal condition, and below normal condition, based on 8 rainfall regimes in Ethiopia. Currently, World Meteorological Organization pushed for hydrological and meteorological offices to use objective forecasts. Before, it uses subjective forecast. WMO recommended to objective forecast. Additionally, the consensus prediction technique didn't take sufficient evidence of being applicable in so many industries. Then, National Meteorological Agency of Ethiopia, it starts to the objective forecast using the Python next generation prediction methods. And the statement of problems are climate model are an important tool for predicting future climate condition, but their accuracy varies depending on origin and season. Evaluating performance of prediction models for various areas and seasons. Therefore, Vital identifies the skillful models are important in region and season. The primary emphasis of this research investigation was to evaluate how effective global prediction model can forecast the key climate variables in Ethiopia, like temperature and rainfall. Significantly, the problem is to evaluate the accuracy and consistency of these systems in forecast rainfall and temperature, and identifying the best predictor domain for the different rainfall seasons over the country. Overall, this research is to improve our knowledge of the strengths and limitations of present global models in predicting rainfall and temperature over Ethiopia, and it provides the best or the skillful models and identifies the forecast lead times. The main objective of this research is the skill of the global prediction models over Ethiopia in predicting rainfall and temperature, and identifies the predictor domain and the forecast lead time. The specific objectives are analyze the skill of global forecast model in predicting rain and temperature, analyze the skill of forecast to different domains to identify most preferred predictor domain, and last objective is to evaluate the influence of lead time on the forecast accuracy. This is a study area of the description of the study area. This is based on location, including synoptic meteorological stations. And this is the climatological of the study area. The first map is this one. The first map is JGS, June, July, August, September. This is the main rainy season in Ethiopia. It experiences for the higher rainfall level in most regions. It is important to supporting the agricultural activity, water resource management, specifically the northwestern, western, and central part of the country. And the right side, February, March, April, May, this is the bulk season, the second rainy season. This is second rainy season in the northeast, central, and highlands of the south and eastern part of Ethiopia. The primary rainfall season over the lowland of south and southeastern Ethiopia in February, March, April, May. This is the temperature climatology of the JJS. The temperature in highland area tends to be relatively mild, and lowland areas experience hotter temperature. The Rift Valley region also experience warm to hot temperature during the rainy season, and the western and southwestern highlands relatively mild temperature due to higher elevation and the forested area. This is the climatology of the study area. For this study, I have used the observed data is the CHIRPS data. It is blended from observed and satellite rainfall data. And using for the TAMSAT and ARC2 data for the observed rainfall. And for the temperature data, I used through Climate Research Unit from the University of East Anglia. And I use for this study, I have tested 9 global climate models. For this study, I use the IRI data library consisting of Hindicast and real-time forecast from global prediction centers. The GCM data catalog is found in seasonal forecast version of PyCPT. It is a machine I use for the machine in PyCPT, Python climate prediction tool, provide seamless access to North American multimodal ensemble and the Copernicus climate change service. For this study, I use for 9 models. This is the abbreviation of all models. The full name of the models are JFDL SPEAR. It is Geophysical Fluid Dynamic Laboratory models. And CCSM4 Center for Ocean Land Atmosphere Studies. And CANCIPS IC3, Canada Seasonality Interpretation System. and NCEP CFS2 Center for Environmental. This is the name of the model. 1 up to 6, 1 up to 5, it is a North American multi-model. It is North American models. And 6, 7, 8, 9, Meteo France, DWD, CMWF, these models are the C3S models. This is the data from which up to where to use. The methodology of the skill analysis and objective by objective. From the first objective in the evaluation of the skill analysis of GCM models, the methodology is assessing the skill of the model for different regions and time scales is important to improve forecast skill and enhance the effective uptake of forecast information. In this objective, the skill of a different global prediction model in predicting rainfall and temperature will be analyzed and compared for 2 rainfall seasons, JJS and February, March, April, May. At the end, the best prediction system will be identified. Utilize of various deterministic and probabilistic skill matrices. The first one is Pearson correlation matrix. The second one is rock area below normal. And the third one is rock area above normal, and ranked probability skill score. I use for this 4 skilling matrices, and the skill of 9 different models have been assessed using the tropical region predictor domains and the 1 month initializing forecast. Then the second objective, analyzing of the effect of a predictor domain. For this, I have using for the canonical correlation analysis method, which is the empirical orthogonal function analysis conducting and independently on both the model hindcast and corresponding to the observation. For the analysis of predictor domain, I have tested or examined 4 predictor domains. It is affected for the Ethiopian rainfall systems. The first one is tropics. The second one is Western Indian Ocean. The third one is Ethiopia itself. And the fourth one is Atlantic and Indian Ocean predictor domains for the 2 rainfall seasons. And analyzing of the effect of time. For this objective, I have used 3 initialized times, 0 months, 1 month, and 2 months lead forecasts, both of them in February, March, April, May, and JJS. For JJS, I used for April, May, and June. For February, March, April, May, I used December, January, and February is the initialized time, and the predictor domain is tropical region. This is a ICPT forecasting system. The result of the analysis of the scale of the rainfall and temperature predicting models are this one. For the map, the red color is the higher scale, and the opposite, the blue color is the low scale I use for this methods. The analysis of the for selecting the first lead time for this evaluation of the skill. These are currently being used by operational climate producing centers such as ICPAC and National Meteorological Agency, used to the tropics, a predictor domain, and the first lead time, the first initialized time. For the JJS, the 9 models skill analysis are shown in this map. The first column is the Pearson skill matrix. The second column is the rock area below normal matrix. The third one is rock area above normal matrix. And the last one is, or the fourth one is the rank probability skill matrix. And the rows are 9 models by ordering. Based on this, the Pearson skill indicates that the CCSM4 and Canadian and CFS V2, CES and GCFS 2.1 and SPS V3, P5 and Meteo France 8 models exhibit high skill over the northern and northeastern part of the country. In rock area below scored, the Canadian CFS V2 and Meteo France, SPS 2, GCFST, SES 5, and GOSS2S models demonstrate high skill over the northern, central, and northwestern and northeastern parts of the country. A rock area above the Canadian CFS V2, SES 5, GCFS 2. These listing models are exhibiting high skill over the northern part. In contrast, SPEAR models and CCSM4 models have low skill. RPSS spatial in the fourth column, all models exhibit positive value over the northern part except the SPEAR models. This means the red color is the skill of the model to predict JJS in Ethiopia. It is high skill. The blue color is it is low skill. Then from this graph, the southern, southeastern, and western part of Ethiopia, the models are predicted in lows. The reason is maybe the southwestern and western part of Ethiopia, it is the skill of the model is very low because of the topography. This is the temperature. In this case, most models are better predicting temperature comparing to rainfall. Then the red color is a good, the models are predict JJS temperature. From this, and the Pearson indicates that SPEAR CCM4 models are predict a high spatial skill in predicting JJS seasonal temperature across the entire country, except for the certain localized areas in the northwestern and southern and southeastern regions. The skill of the models are low. The other places are especially the northern eastern. Okay, is a good skill. Okay, this is okay. This is the same procedure. This is February, March, April, and this one is the temperature. And the analysis of the skill of the second objective is this one, the predictor domain. I have used in these 4 predictor domains. Based on this, the tropical predictor domain, the Western Indian Ocean predictor domain, I have tested for this. Finally, I will discuss for the conclusion for this one, but the methodology, the result is like this. This one is as the Ethiopian predictor domain and the Atlantic and Indian Ocean predictor domain. This one is the February, March, April, May seasons. I use for the 4 predictor domains and test this one. And also use the Ethiopian predictor domain, Atlantic and Indian Ocean predictor domains tested for this one. Then the examination of lead I have used for 3 initialized lead timers. Based on this, I have tested for the JJS April, June, and May. For February, March, April, May, I have tested to December, January, and February. From this analysis, I have get for the final results or for my abstract or my conclusion, the models, North America multi-model and C3S models in forecast JJS and February, March, April, May seasonal rainfall and temperature using tropical region. The Canadian CIPS, I3S, ECMWF, DWD, CMCC, and Meteo France models demonstrate a Pearson correlation and rock scores that exceed 0.5 and RPSS scores greater than 30, particularly over central, northern, northeastern, and northwestern, and specific eastern region of Ethiopia. So these models are a best predictor for these areas for JJS. On the other hand, JFDL SPEAR CCSM4, GEOSS2S, and CFS-V2 display low performance for predicting JGS seasonal rainfall pattern over the central, northern, northeastern, and northwestern specific eastern region of Ethiopia. So in general, for the skill of the model analysis in JGS, low skill to predict JGS rainfall season over southern, southeastern, southwestern, and western half of Ethiopia. This could be due to the low resolution of GCM forecasts that are not able to resolve the effect of topography in these high topography areas. GCMS lacks the ability to resolve well the small-scale processes that are crucial for the local climate. During the February, March, April, May, GFDL, SPEAR, Canadian SIPS, ICS, ECMWF, GWD, CMCC, Meteo France models show high promising performance in forecasting the seasonal rainfall over southern, eastern, central, and eastern part of Ethiopia. On the other hand, CCSM for GEOSS2S and CFS2 low skill in the forecasting February, March, April, May seasonal rainfall over southern, southeastern, central, and eastern part of Ethiopia. For February, March, April, May, the western half of the country across the product areas, it is very low a skill for the models to predict. The main reasons are farm is not the main rainy season. Over the western part, Ethiopia is dry season. It has been noted that the performance of the model in forecasting below normal rainfall is higher than the above normal rainfall. The models are predict the dry is higher than to the wettest
Want to leave some time for questions, so
seasons.
so maybe just can we allow you to stop at this point and allow some questions? Maybe a brief concluding remark.
1 minute. Okay, 1 minute. Okay. Then in the temperature, these models are, the first models are good ski. The same to finding the rainfall, temperature, this one in different seasons. This one is the skill of the model, the predictor domain. For my analysis, I tested 4 domains. The tropical ocean is the best predictor domain for in the Ethiopian JGS seasonal rainfall prediction. Even for February, March, April, May, the tropical region is the best predictor domain. And for the initialized time for JGS, 1 month lead is better, but 0 month lead is even good. But for agricultural activity, for the planning, 0 months is not good. Based on this, the 1 month initialized forecast is better in JGS, and February, March, April, May, even 1 month initialized forecast is better for my finding. This is a recommendation for scientists, the recommendation for users. Thank you very much.
Thank you. We have a question already on the chat, so hopefully, are you able to read it and respond?
Okay.
Do you have any other questions? You've seen the question.
Still now, I have not seen.
Maybe Moses, you can just ask if you're still with us.
Yes, I'm here.
Okay.
Just what
Okay.
I want to operationalize the word skill. What do you mean by the skill of a model?
Okay. Yeah, the skill of the model means the prediction skill. For example, ECPAC or any organization to the climate for prediction centers, it uses different models. Then first to combine the ensemble or to give the prediction, firstly to analyze the skill, the ability, what is this, how much the skill of the models to predict JGS for in Kenya, for in Ethiopia, for like that. the skills are
Asante.
analyzed based on correlation.
Sorry to interrupt you, but you cannot
Okay.
define a word with itself. So when you say the skill means the skill, it's not helping. What is the skill without using the word skill? I'm trying to get that part.
The skill of the models are different to model to model.
So what is a skill? How do you know? How do you measure a skill or a model?
Based on different skill matrices. For example, I have used 4 skill matrices. The first one is
Which are these
Pearson
metrics?
correlation, Pearson correlation, ROC, and ranked probability RPSS.
Okay, I'll just not to extend too far, just go think through what it meant by the skill of a model. It's a new concept. I've not heard that before. I know we usually are conversant with, say, the accuracy or the reliability of models.
Accuracy.
Is it accuracy?
Yeah, the skill of the model, it gives for the accuracy of the model. Yeah.
Oh, good. Maybe for consistency with the rest of the community in this area, you could use terms that are more standard so that we can be able to appreciate the work. Then I have a few other questions then. There were 3 in the chat. What's the implication in practice of having several models that are skillful in different regions? You demonstrated that some models were more skillful in other regions. So in practice, if we were to take this work forward to the Meteorological Association, would you give them 10 models to use and tell them, for this one, use in the northern region, this in the northwestern? And then that's the first, what's the implication in practice? Then, did you examine why some models were more skillful or less skillful in some regions? And then finally, did you check whether the issue could have been the data coming from the different regions, so that some models are better with data of a certain kind as compared to others, so that then they end up being more skillful in some regions compared to others? Thank you.
Yeah. Thank you very much. Thank you very much. Yeah, even my analysis, for example, in Ethiopia, uses for the subjective forecast. It started since 1 year, but not analysis, not checking the skill of the models. Only use 9 models due to the ensemble, multimodal ensemble forecast, and gets output and give the forecast. Even ECPACs are like that. But before that, if you check the accuracy or the skill of the model is important. For example, in Ethiopia, JGS, only the northern and northeastern and central part of Ethiopia, the models are a good accuracy. But the western part of Ethiopia, it is very limited accuracy. Then it is the best thing is it's checking for the accuracy of the model in different regions is better. Thank you for your comment.
Okay, so I think we are almost out of time, but let's appreciate the speaker. Yes, so I think this is the first of a series of four presentation meetings. I think I shared the schedule earlier. So hopefully we'll be running every Friday for the month of September. And I think I would like to thank all of you who've stayed up to this very end, and also to our speakers. Thank you very much for all the good work. I think maybe we will just end it there and meet next time. Thank you very much.
Thank you very much. Okay.